Right, final example from this chapter, moments, is example 12. So example 12 talks about a non-uniform rod that we have to draw for ourselves. And what we need to do is we need to have a look at what's going on. So we draw the rod AB. First thing we need to do, mark on clearly A and B. Then we've got its weight 40 newtons. It's non-uniform, so we don't know where the centre of mass, we don't know where that 40 newtons will be acting. Its length is 10 metres, and AC is 3 metres, and BD is 2 metres. So AC is 3, and there's going to be a cable. I'll draw the cables in a different colour. So there's going to be a cable coming up here. This is from C. And then BD is 2 metres, so over on this side we're going to have a D and another cable coming up. Right, so think of a light being suspended to the ceiling. And then we fill in all the lengths that we know. This is a 3, this is a 2, it's 10 in total, so we must have 5 between them. It says that a weight of 25 newtons is hung from the rod at A. So 25 newtons over here, and the rod is on the point of rotating. Find the distance of the centre of mass from the rod from A. So again, let's mark on the centre of mass. So this is 40 because the weight is 40, but we don't know how far it is. That's what we'd like to find out, how far from A that is. So let's just call this X. Right. In terms of the forces that the string provide, they're exactly like those little triangular supports. So they will have tensions, so I can call this TC, TD, right, both stopping it from falling. Right, so although it's not being supported from underneath, it's being supported by above, the overall effect on the problem is the same. Given that it tells us it's on the point of rotating is another way of tilting, the thing that it doesn't tell you is where it's tilting about. So you have to think about it for yourself and use your common sense to work out which point it's going to rotate around. So here we've got the 2 strings. If you imagine this is being held from above, right, and then I put something on here and it's going to tilt upwards like that, isn't it? Now what does that mean then for the tensions? Well, the C is still going to be supporting it, isn't it? But what's happened to the string here? Well, because it's moved up, because the object and the rod has moved up, it's going to make the TD go slack. So there's no longer going to be any tension in the string, just like when we had something it was resting on, there was no longer any reaction force there. Well, the tension at TD is going to go slack. So what happens when we're on the point of tilting, this whole rod's going to tilt up like this with TC. Maybe it's easy to demonstrate it on here. With TC on there, it's going to tilt up like that. And TD is not going to have a force there anymore, it's just going to have some slack string, a slack cable, but TC will still be acting. So because we're tilting, I'm going to cross it out here, tilting, there's no force at that point anymore. Right, that means that we're ready to go about and have a go at this. So again, 2 options, same 2 options as the entire way through this unit. The first one is we can resolve vertically. This tells us that T is equal to 25 plus 40, so T is 65 newtons. Right, that's at the point of tilting. So obviously there's more pressure put on it because there's no longer a tension here holding it up. This has got to hold everything up itself. We didn't actually want to find T though, right? So we found it, but this question didn't ask for that. What we want to do is we want to find out X. And there's 2 ways to do it. You can either take moments about A or C. I think are the obvious places to take moments about. If you take moments about A, it'll be nicer. I've got the X there. In fact, I'm going to do both, in fact. So let me show you how it would work if we take moments about A. All right. So if I take moments about A, we've got the 2 things. We've got the TC, right? If we're fixed, imagine it was fixed at A, right? It would be doing a moment about that, because we're still in equilibrium even though we're on the point of tilting. So that would be TC making it anti-clockwise. So we've got that 3 times T which is equal to 3 times 65, which is 195 Newton meters. That was going anti-clockwise, and then the 40 would be pulling it down in the clockwise, so 40x Newton meters, and that would be clockwise. So then what we can do is we can put them equal to each other because it's an equilibrium. So 40x equals 195. So x is going to be 4.78, so I think it's 4.875 meters, and that's how far away from A it would be. I just want to demonstrate quickly what would happen if we'd have actually taken moments about C instead, because that's a bit more intuitive, right? Sometimes people struggle with the idea of you're taking, even though we're on the point of tilting about C, so that would be the pivot C, right? We've taken moments about A. We can do that because it's an equilibrium. It doesn't have to actually be a real pivot point for us to take moments about it. But let me just show you how moments about C would have worked. So moments about C, this time we wouldn't be using the TC, and this one would still be pulling us clockwise, but this one would be pulling us anti-clockwise. So the anti-clockwise one is 3 times 25, which is equal to 75 Newton meters. Meanwhile, this one, and this is where it gets a little bit tricky, right? If we've put the x in a place like that, either we could relabel it and call x just between C and 40, and then think about when we do the solution actually what the distance of the centre of mass from rod A is, or we can leave it like that, but we can use a little bit of algebra. So 40 is definitely our force, right, pulling us down, but the distance is x minus 3. Right, if that's x there, the full distance from A to 40 and from A to C is 3. That makes this one x minus 3. So we just have to do an x minus 3 here, Newton meters. Again, they're going to be the same. So 40x minus 120, expanded the bracket, equals 75. So 40x equals 195. And then we divide, right? And hopefully we get 4.875 meters again. Right, again, I've been a little bit naughty. I'm not giving it to 3 significant figures, but when it's such a lovely answer like that, I think it's difficult to then round it at the end. So x is 4.875 meters. Make sure, right, that we write that out. So the distance of mass from the centre of mass is 4.75 meters from A. Right, that's our final answer for full marks. Right, then you can have a go at exercise 4E. Right, there's 7 questions. I would advise you to start off by doing the odds. Right, you have to draw them all for yourself. Well, actually, no, you do get some diagrams. You have to draw most of them for yourself. Have a go at them. If you want more practice, do the evens. And of course, there's also the mixed exercise at the end of the chapter with some really tough, interesting exam questions. But obviously, that's all to come on the CASs as well. So you've got that to look forward to. Okay, but I hope that's all right. That's moments. Hope it makes sense. If not, questions in the forum. I'll get back to you as soon as I can.